Okay, welcome to lesson 3 of unit 6. We're still focused on limits and continuity, and one of our main things we're going to do here are objectives right here. One is to recognize when a limit does and does not exist and evaluate that limit specifically at a certain value. So when x approaches a, which is a specific value, and then we're going to classify discontinuities. We're either going to have a point discontinuity, infinite discontinuity, or jump discontinuity. But before we do that, we're going to do a little warm-up of what we've done in the previous lesson. So you might want to pause now and try this on your own. So I'd go ahead and do that. Try to do this whole warm-up on your own. So if you completed this, you should have gotten a whole at 2, 5 and a whole at negative 2, 1. I factored the numerator by grouping, and x squared minus 4 factors to x minus 2x plus 2, so you should see that. And then both of those canceled, which means you had 2 wholes there. And then we end up with the line, so there isn't a horizontal asymptote. As x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity, right? So here we have that. That's our end behavior. Therefore, there is no horizontal asymptote. Then I determined my x and y intercepts. So we have those x and y intercepts by plugging in 0 for y or 0 for x. And then finally I sketched my graph. So that is what you should have had for the warm-up. All right, so let's move on. So here we have the methods and meanings, a little tidbit of information. When does a limit exist? So it says we say that a limit of a function exists at a particular value a if the limit from the left of a is the same as the limit of the right of a. So your left-hand limit must equal your right-hand limit. So when you're approaching a specific value, so let's look at this one up here. We're approaching negative 2 from the left, we're approaching negative 2 from the right. When we approach it from the left and from the right, we got the same value of 1, right? So when we approach negative 2 from the left and negative 2 from the right, we got the same value of 1. Therefore, there is a limit there. That limit does exist, and that value of the limit was 1. So here is what we wrote up there, where c is a real number. The limit as x approaches a particular value from the left and a particular value from the right. If it's the same value, then that means the limit does exist. It does not mean that it has to be defined. Oops, that's up here. Note, the function itself does not need to be defined in order for a limit to exist. As such was up here. It's not defined. It's a whole. It's not defined here. F of negative 2 does not exist, which is what we wrote here. But it still has a limit, right? So if your left-hand value and your right-hand value as it's approaching as it's approaching x is the same, then that means you have a limit there. This information right here. That's right. Moving on. So exercise 1. We have a piecewise function here. We've graphed the piecewise function for you already. So the value of x plus 1 as x is greater than 0, so not equal to 0. So you plug in 0, you would get 1, but it doesn't include there. And then you plug in 1, you get 2, etc., etc. So that's the top portion of the piecewise function. Here it does include 0. So when you plug in 0, you get negative 1. It's inclusive, so it's a closed circle. And then this is what the rest of that graph would look like. So now you're just going to see if you understand the limits. So it says the limit as x approaches negative 3 from the left for this function. So 1, 2, 3, we're approaching negative 3 from the left, which means we're coming in from this direction, right, from the left-hand side, which means it's these y values here. So what is the value that it's approaching? It's approaching 2. The limit approaching as x approaches negative 3 from the right, so we're coming in this direction, approaching negative 3 from the right. So in other words, you're going to be climbing up the red graph, and once again, that value is approaching 2. Because your left-hand limit and your right-hand limit are equal to each other, the limit as x approaches negative 3 exists, and that value is 2. All right, if we were to do, oops, sorry. I was trying to erase there, but that's not working. I don't know why. So if we're trying to do the same thing for the next value, so let's do this side. So the limit as x approaches 0 from the left. So we're approaching 0 from the left, so that means it's going down this graph till it gets here. So that value is -1. And then we're doing the limit as x approaches 0 from the right. So my values for my x are approaching 0 from the right, which means it's coming down this graph and it's ending here, which is at +1. Because your left-hand limit and your right-hand limit do not equal each other, the limit at 0 does not exist. Sorry, and I'm going to change this. We're going to pretend that just says 0. I don't think that negative sign should be there. So the limit as x approaches 0 does not exist because these two things do not equal each other, because your left-hand limit and your right-hand limit do not equal each other. So that is according to the previous page, where that's the case. Okay, so let's move on to exercise number 2. We have another piecewise function. We've graphed it here for you. When x is less than 2, it's going to be this graph here. When x is equal to 2, it's going to be exactly 1. When x is less, or sorry, I did it backwards. This is less than 2, my bad. This is greater than 2, sorry, and the blue dot's equal to 2. Okay, so let's check it out. The limit as x approaches 2 from the left-hand side. So we're approaching 2 from the left-hand side. So we're approaching 2 from the left-hand side. So we're coming down the graph and we're ending up here. So if we approach 2 from the left-hand side, we end up at the value of 4. If we approach 2 from the right-hand side, we're approaching it this way. So we're going down this graph, because all the way at positive infinity, it'd be way up here on this graph. It'd come down, 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 and down, and it'd end here. So once again, we are at 4. Because your left-hand limit and your right-hand limit are equal to each other, then that means this limit does exist. And specifically, when they equal, the value of that limit is equal to 4. I know that seems strange because it's defined down here at 2, but it doesn't matter. Remember, your limit exists even if your left-hand limit and your right-hand limit are the same. Doesn't matter if it's defined at that point. That is irrelevant. It's what's getting closer and closer, the y value that it's getting closer and closer and closer to, if you follow the graph from the left-hand side and the right-hand side. Okay, now we're going to evaluate some limits. So exercise 3, it says evaluate the following limits algebraically. So we'll ask you to do this. We want to see if you can do this algebraically. If the limit does not exist, write D and E, then confirm your result with the graph. So we're going to pretend the graphs aren't there, and we're just going to evaluate the limit, because that's what you would do on a quiz or test. You wouldn't have the graph, you wouldn't have your graphing calculator, so we would just ask you to do it algebraically. So we want to know, what would the limit be for this particular graph as x approached -1? Well, this is a linear function, right? So you could imagine that, and it's right over here, I guess. Maybe it's helpful to look at the graph for now. So in that linear function, we're approaching -1, right? So it's -1. It doesn't say from the left or the right, so it's both. So it's from the left and the right. So we're approaching -1, we're approaching -1. Well, what is that value? Well, you would get that value by simply plugging in -1 in for x. And we get a value there, and that value is -6. So if you were to look at this graph and approach -1 from the left and to the right, did we get -6 as our answer? Yes. So the limit as x approaches -1 for this particular function, x minus 5, you would get a y value of -6. For letter B, so that's the first thing we're going to do. It just means plug in 3 for our x, right? So it looks like we're going to do 3 divided by 3 minus 1. So in this graph over here, which is a rational function where x cannot equal 1, which means we have a vertical asymptote, which here it is, a vertical asymptote of 1. We have a horizontal asymptote of 1 as well. We'll talk about that more specifically later. But as we approach 3 from the left and from the right, so we approach 3 from the left, here's 1, 2, 3. We approach 3 from the left, 3 from the right. What is this value? So you can't really tell from the graph because it's not specific. So we plug in the number 3 to figure it out, and that value would be 1.5. And it looks graphically like it is right there. So the limit exists. It's the same from the left and from the right. And that value particularly is 3/2 or 1.5 or 1.5. So this looks pretty easy. It looks like all we have to do is plug in the number. So the limit as x approaches 2. So I'm going to plug in 2. I'm going to plug in 2. Oh, but sure enough, what happens? This is not allowed. It looks like the limit does not exist because we have a 0 in the denominator. But that may not be true. We need to check it by factoring. So instead of just plugging right in, if you have a quadratic, you should factor first. So I'm going to take this same limit as x approaches 2, but I'm going to factor my numerator and my denominator. Well, my numerator can't be factored, so I'm just going to factor my denominator. And then what you'll see right away is that we can cancel one of the factors. So obviously there is a hole in this graph at x equals 2 because it's a canceled factor, and we learned in our previous lesson that there's a hole there. So that is why it looks like there may not be a limit when we plugged it in, because there's a hole. So we know that it's going to tell us that a y value does not exist. However, we can still calculate that hole by plugging in the 2 here and see that the hole is at 2/1/4. So once you cancel that, now you plug in 2, and so we can see the limit as x approaches 2 from the left and from the right, and we can see here from our graph as it approaches 2 actually does exist, and that value is 1/4. So that is 2,1/4. So the limit as x approaches 2 is 1/4. A hole. All right, let's try another one. So what's the difference? This looks like it's the exact same problem, but it isn't, because instead of as x approaches +2, we have x approaching -2. So again, we have the same issue. When you plug in a -2, what happens to our denominator? We get a 0. So it looks like the limit does not exist, but that's not necessarily true. So we have to factor it first. So when I factor my numerator, I can't factor it, it just stays the same. I factor my denominator, then I cancel the common factor, which is x minus 2, and now I will substitute in my -2. So I get 1/-2 plus 2. Okay, now that I did factor, I still get a 0 in my denominator. So actually now I have proven that in fact this limit as x approaches -2 does not exist. And we know it does not exist because it's a vertical asymptote. And the right-hand limit is going to +∞, and the left-hand limit is going to -∞, which is not a particular value. Therefore, this does not have a limit, and the limit does not exist. So the answer is does not exist, and you would just write that. But you should show work to support your answer. Okay, letter E, it's a quadratic, so my first instinct is to factor. I'm not even going to plug right in anymore if I see a quadratic. I'm going to factor it. So my numerator is 2x minus 3. My denominator, this is kind of a hint, I would say. If you have 2x minus 3 in the numerator, it's probably going to be 2x minus 3 in the denominator, which means I need to have a +2 over here. I'm going to check it, +4x, -3x. That gives me my positive x in the middle. So yes, it all works out. And this is how it factors. Once I factor it, my factors cancel. So now I'm going to take the limit as x approaches 4 for 1/x plus 2. This now means all I'm going to do is take the 4, plug it in. So I'm going to get 1/4 plus 2, which is 1/6. So there I have it. And I can see as x approaches 4, 1, 2, 3, 4, from the left and from the right, it does exist, and that value is just simply 1/6. Or here I have it, where I can show you or I show you what it is. So this is my answer. The limit as x approaches 4 is 1/6. Finally, this last one looks a little yucky. If I plug in, I get 0 over 0, which looks like it does not exist, but that's not necessarily true. I need to factor to see if it does exist. Okay, wait a minute. How do I factor this? Well, it's the difference of squares, believe it or not. So there's two ways of doing this problem. I'm going to show you both ways. One is to factor my denominator. Instead of x times x, I'm going to do root x times root x to get x, and I'm going to do minus 3 plus 3 to get 9. This is, in fact, the difference of squares, right? Usually you would see something at x squared minus 9, which is x minus 3x plus 3, but instead we took away the squared, so that means we're just going to do root x times root x to get x. Okay, so now these factors cancel, so I'm just going to plug in my 9 here. So I'm going to get 1 over the square root of 9 plus 3. So that's 1 over 3 plus 3. So my limit actually does exist, and that value is 1/6. I'm going to show you another way to do this because you are going to use it at a different time, and that is to take this original problem. So I'm going to rewrite it. As x approaches 9, we have the square root of x minus 3 over x minus 9. So another way of approaching this problem, excuse me, would be to multiply the numerator and the denominator by the conjugate. So when you see this square root sign right here, you want to multiply by its conjugate. I think you have a problem like this in your homework. So I'm going to show you now so you don't get confused later. So when I multiply by the conjugate in my numerator, when I simplify that, I would get x minus 9, because root x times root x is x, and then our inside and outsides cancel, and then negative 3 times positive 3 is negative 9. And then in my denominator, I still have my x minus 9 right here, right? I should have parenthesized that. And then I have my root x plus 3. But now with your x minus 9 in the numerator and your x minus 9 in the denominator, those cancel, and I'm actually left with the exact same scenario as I had over here in my blue part. And I would just plug in my 9 and I would get the same thing, which is 1/6. So whether you multiply by its conjugate or you use a difference of squares, you're going to get the same answer for your limit. All right, so we're moving down here to this when is a function continuous. Now we're going to talk about continuity. So we say that a function is continuous at a point x equals a if all three of the following conditions are true. Number 1, the limit must exist, which means your left-hand limit must equal your right-hand limit. In order to write the limit as x approaches a specific value, your left-hand limit must equal your right-hand limit. In order for the function to be continuous, remember we're talking about continuity right now. That means you don't have any asymptotes or holes or anything in the graph. So in order for it to be continuous, you must have no holes, which means every value must exist, right? So f of a must exist. So the function has to have a y value at that particular a value that's given, right? So that must exist. And then finally, the limit as x approaches a for the function has to equal f of a. So you can't have a hole again or an asymptote. So these three conditions must be met in order for the function to actually exist. All right. Okay. So we have three different types of discontinuities. We have point discontinuity, we have infinite discontinuity, and we have jump discontinuity. And we have pictures here of the three different types of discontinuities. So a point discontinuity is discontinuous at a specific point. Like here, you can see it's discontinuous at that specific point C. Why? Oops. Because the limit as x approaches that value c of the function does not equal f of c. So the limit is actually here coming in, let's say this y value is 1 and this y value is 2, the limit is actually 1, and that limit does not actually equal the defined value. Therefore, this is discontinuous at point C. Infinite discontinuity is when you have a vertical asymptote, right? So this is when you have a vertical asymptote. This is when you have a hole in your graph. Point discontinuity is when you have a hole in your graph. Infinite discontinuity is when you have a vertical asymptote. So it's discontinuous at x equals c because the limit as x approaches c from the left does not equal the limit as x approaches c from the right. So when the limit as x approaches c from the left does not equal the limit as x approaches c from the right, then the limit does not exist. And if the limit does not exist, then that means we have a discontinuity. Particularly, we would say those are going to negative and positive infinity. Jump discontinuity is when you are following along the graph and then you have to pick up your pencil and go somewhere else. And it's just like it's like a piecewise function, right? So this looks like a piecewise function. So jump discontinuity is discontinuous at x equals c because the limit as x approaches c from the left and the limit as x approaches c from the right do not equal each other, which means the limit as x approaches c also does not exist. So usually for your vertical asymptote or your infinite discontinuity, these values are approaching positive or negative infinity, and they may not equal each other. So you have a vertical asymptote or an infinite discontinuity. Here, they're just jumping from one to the other. So your limits are not gonna, your left-hand limit and your right-hand limit are gonna be different. So that means the overall limit does not exist. This is hard to explain in a video, so you might want to go ask your teachers about this as well to get a little extra help, because I'm having a hard time explaining all of this, so you'll have to see your teachers. All right, exercise 4. It says calculate the limit as h approaches 0 for f of x plus h minus f of x all over h if f of x is 4 over x. So if we just plug in 0, that's what we learned. Let's just plug in a 0. Well, it's not going to work, because you're going to get f of x plus 0 minus f of x all over 0. Well, this is going to be f of x minus f of x over 0, which is 0 over 0, which does not exist. Well, we know that's not going to work, so we're going to have to think of a way to simplify this so we can find out what h is approaching. So we have to first, so the limit, actually I'm going to color coordinate this. The limit as h approaches 0 is f of x plus h. So f of x plus h means that we take the x plus h and plug it in for x. So that is 4 over x plus h. Right? If I said f of x equals 2x plus 1, calculate f of 1. Remember, we're substituting in the 1 for x. So if I'm calculating f of x plus h, I'm substituting in x plus h for x. So that's essentially what I just did in this very first step. Right, I substituted in x plus h into x. Then I'm subtracting f of x. Well, f of x is just 4 over x. I'm putting that whole thing over h. Right, so that's step number 1. The limit as h approaches 0. I've just substituted in x plus h and then left the f of x and put that in there. Now we have an improper fraction, or a complex fraction. So I want to try to eliminate these denominators right here. So I'm going to multiply the numerator and the denominator by the common denominator of these two fractions up here. So now I'm going to simplify that. So here, if I were to multiply this red section, 4 over x plus h times this, x times x plus h, your x plus h's would cancel, right? And then I would be left with, let me write this again, because we're still doing the limit here. We haven't plugged in 0 yet, so we're still calculating our limit each time. So my x plus h's would cancel, and I'd be left with 4 times x. So this would cancel, and this would cancel, and I'd be left with 4 times x only. For my blue part, my x and my x would cancel, so I'd only be left with negative 4 times x plus h. And in my denominator, I am still left with h times x plus h, right? So nothing cancels in my denominator, so I've got to put it all down there. So now I'm going to simplify. So this is the limit as h approaches 0. I'm going to try and simplify this. This is 4x. I'm going to distribute here minus 4x minus 4h. And that's all over hx times x plus h. So here you can see that my 4x's cancel. So now I have the limit as h approaches 0 of negative 4h all over hx times x plus h. But now what happens to my h here and my h here? They can cancel each other out. Almost done. I get the limit as h approaches 0 of negative 4 over x times x plus h. So now my last step is to take the 0 and plug it in for h. And look, we no longer have an undefined denominator. We don't have 0 in the denominator. Instead, we get negative 4 over x times x plus 0, which is negative 4 over x squared. So this answer right here for the limit as h approaches 0 for the function 4 over x is going to become negative 4 over x squared. Okay, our last question here, you're going to fill in the table. I'll do the first one with you, and then you can try to fill in the rest and then check your answers online. And I'm not going to talk you through everything. It's going to take too long. This video is already long enough. So a sub 1, so you can see across here it's a sub 1, a sub 2, a sub 3, a sub 4, etc. These are C1, C2, C3, etc. So we have an input value of x equals a. So here's my input value, a sub 1. The output value would be what? Well, when I put in a sub 1, I get C3. So this is C3 right here. My left-hand limit, as I come from the left, oh, don't miss this part down here. This is coming from the left of a sub 1. It's approaching, when I come from the left, I actually get a value of C1. When I come from the right, that's coming down this way, I get a value of C3. If your left-hand limit and your right-hand limit are different, does the limit exist? No, the limit does not exist because my left-hand limit and my right-hand limit are different values. They're C1 and C3, so my limit does not exist. Is this graph continuous at A1? No, you can see here it has jump discontinuity, so no, that is not true. Why is it not true? Is it because the value at A1 does not exist? No, it does exist. It has a closed point right here. Sorry, I've marked all over this. So it does exist. It has a closed point. Is it because of B, the limit as x approaches A does not exist? Well, as soon as I have this does not exist, then yes, it is B. All right, try the rest on your own. See how you do. Go see your teachers or one of us pre-calc teachers if you have a lot of questions. See you later.